So we spent a lot of time looking at the potential energy and electric potential and how they relate to kind of concepts of work, force, and electric field. Well, in this case, we are going to now deviate from our primary discussion, which was of point charges. And that's because we saw in our previous unit, when we're looking at electric fields, that we could have a wide variety of different objects. So there's two approaches that we take for these. We can either find it directly using calculus. So kind of what we did with like our line of charge. So if I had a line of charge here, and I want to find the electric potential at some point in space, I could break this into infinitesimally small, tiny little pieces, each of which are going to contribute some sort of potential dV. So based on the distance r that it's at, there's going to be some little tiny potential. That's potential, that's not volume, gets a little confusing. Some voltage element, I guess you could call it, due to this little tiny amount of charge. And then you could set up that expression, and then you could integrate from one side of the rod to the other to figure out what that would be. Now, this is actually a lot easier than when we were working with electric field, because once again, the electric potential is not a vector. So we don't have to worry about X and Y components, sines, cosines, and all that kind of business. So that's actually a little bit easier than it is before. So that's one way we could do it. That was like our first derivation packet with electric fields. The other way we could do that is by using Gauss's law or some other method to find the electric field. So if I have a known electric field, which I could find by using Gauss's law or from a given formula that's on the formula sheet, if I know the electric field, then I can use the relationship between the electric field and the potential in order to find my potential difference, my voltage, or the electric potential at a point. So those are kind of the two ways that you're going to do. Now, your derivation packet is going to have you practice kind of both methods, where you'll start with Gauss's law, derive the electric field, or start with an electric field equation that we had found in the previous derivation packet, and then apply that and then find the potential, add on. We will also do some examples where we just find the potential straight up, and then not worry about the electric field at all. So those are kind of the two strategies that we're going to work through. So I have a separate video kind of digging deeper into this diagram, and this diagram is also on your the front of the derivation packet. So this is essentially our roadmap for how we can get back and forth between those different bits. So the two that we are going to be concerned with most is going to be this one right here, where we go back and forth between the electric field and the electric potential, because your electric field is negative the derivative of your voltage with respect to whatever your position is. It could be 1 dimension, 2 dimension, 3 dimensions. It could be a radius. It can be X, Y, Z. All sorts of different things, or starting with your electric field, and you can also find your potential going the other way. So that gives us the ability to go back and forth between those. So if you're ever stuck and you have any one of these values, you can use these equations to go through. Now, this diagram is not on your formula sheet. The equations are in at least one of the formats, but this diagram isn't. So it's something that I would kind of ingrain in your head, practice working through, because it can help get you through a lot of situations in which you're stuck. So I do want to show how this is used through two different methods. So the first method is going to be finding, using Gauss's law to find the electric field, and then using the electric field to find the potential. And then I'm going to work it again, this time actually just straight up finding the electric potential. So with that, when we look at these parallel plates, we are going to assume an ideal situation. So real parallel plates have the positive charges primarily focused on the inside, but there are some out here on the outside. And then same with the negative charges. They're going to be focused towards the center, but there's going to be some still here on the backside. What that ends up causing is that ends up causing some curving of the electric fields, because you're going to have field lines coming out and going around from everywhere. When we are working these problems, we are going to assume that essentially the size and area of those plates is so large compared to the separation distance that I can ignore all of those edge effects. That basically all of the positive charges are on the inside of my surface and all of the negative charges are on the inside of the surface. So that means there is no electric field outside, and basically these plates just kind of continue on. So we're only looking at something like in the dead center here where the electric field is perfectly uniform. We are going to assume that the surface charges have a value of positive sigma and negative sigma. So remember that sigma is the charge density. It's going to be Q over A. So in this case, we're going to assume that that charge density is constant across those entire surfaces. So we've got this charge set up. So what I'm going to do is I'm going to just kind of remind ourselves of how we would work through and find the electric field first. So if I was to find the electric field first and then find the potential difference, what I would do is I would create a Gaussian surface. Now that's kind of hard there, so I'm going to kind of blow up kind of the thickness of these plates right here so you can kind of see them better for what I'm going to do. Now, when I'm trying to do Gauss's law for parallel plates, I know that there's going to be this electric field going through, and I'm assuming that the positive and negative charges are just in the surface. Now, technically, they're not outside the object like they're shown here. They're in that thinnest outer layer of my surface. So with that, I need to choose a Gaussian surface. When we did a single plate before, we did essentially a cylinder. And you could do a cylinder or you could do a rectangular prism. So we're going to assume that we have a cylinder here, and I'm going to choose a point that my cylinder is intersecting the dead center of these plates. So in all dimensions, it's going to be the dead center between. Now, I don't actually have to assume that because I am assuming that my electric field is uniform, so it's constant everywhere. So it really doesn't matter where I do it. But to be more robust, it's best to do it in the dead center of the plate because then you're furthest from all of the edge effects that could possibly be affecting it. Now, what is happening here is I have created my surface so that one end is actually inside the material of my conductor. So because I'm inside the material of my conductor, there's no electric field at all inside that material. But I am going to have an electric field that is unknown in the gap between. Now, I have a second plate, and I'm actually completely ignoring it. And you might be going like, how can I solve this problem without having a second plate there? Well, the reason we can do that is because if I was to actually try and draw a Gaussian cylinder that included both plates, what would happen is my enclosed charge would be equal and opposite. It would have a positive and it would have a negative charge that would be equal and they'd cancel it. So I'd actually have no enclosed charge. There would be no electric field. So I need to make sure that the point that I am choosing is actually in the gap in between the plates themselves. So what I have is then basically electric field. This is a circle, and I have an electric field coming out of it, and I have my dA vector coming out of that area. If I look up here, my dA would be coming that way, but there's no electric field there, so I can ignore that surface entirely. And then on the third surface, if I'm picking a section in here for dA, no matter where along the sides of that cylinder, how it wraps around, when I'm inside, there's no electric field, so I can ignore it. When I'm outside, that dA vector is perpendicular to the electric field. So the only surface that has electric field going through it is this one right here. Additionally, for Gauss's law, I have to consider the enclosed charge. So the enclosed charge is actually going to be, once again, a circular surface here that's going to have some charge dq. That Q enclosed is going to be some small amount of the charge of the overall thing, and that is going to have a positive charge based on my surface right there. So if I'm setting up Gauss's law tells me that the integral of E dot dA is equal to Q enclosed over E naught. So because in this section right here, E is parallel to dA, I can rewrite that as E times A. And they're all constant and everything like that, so I don't need the actual integral. It's just going to be E times A. And so that's going to be Q enclosed over E naught. So with that Q enclosed is going to be kind of some fraction here. I don't actually need to integrate on that one. I could just call it like Q enclosed. But if I was needing to integrate, I would use the dq. So what I would do is I'm going to set up a ratio. So I've got sigma, which is known. So sigma is, I could write Q over A, but I actually don't know the whole area of the plate, and I don't know the total charge on the plate. So I can't actually use that portion. But I do know that sigma is going to be Q enclosed over A enclosed. So whatever that little tiny surface area A is. So I'm just going to call that A. Okay. And I'm going to assume that that A here is the same as the A for that surface. So I'm just going to say that sigma is going to be Q enclosed over A, where A is just the area of that surface. It's not the area of the whole thing, just of that little circular surface. So Q enclosed is going to be sigma over A. So I'm going to come back over here and sub in. So I get E times A is equal to sigma times A over E naught. And I see here that the A's are going to cancel. So E is going to be sigma over E naught. And that is going to be the electric field here between my parallel plates. So that's not my goal. My goal is to find the electric potential between the parallel plates. So what do I do? All right, so what we want to do is we want to find the electric potential between the two parallel plates. So I'm going to define that electric potential difference from A to B. So I'm going to assume that I have plate A is the positive plate and plate B is the negative plate. So I could write this as V at plate B minus V at plate A. So that is what I'm saying in terms of setting that up. So I know that my voltage, delta VAB, is related to my electric field because it is equal to negative the integral of E dot dr. Okay, so I don't need to work in terms of R, but I could write this in terms of X. So I could have my X equaling 0 here at the plate. And I'm going to use the separation distance between these D. And I'm going to define that variable right there as the separation distance between them. So I'm setting up a coordinate system. So my delta V from A to B is going to be negative the integral from A, which is going to be at a position of X equals 0, to B, which is at a position of D, and it is going to equal E dot dx. Well, the way that I have defined these, my electric field and X are going to be in the exact same direction. And because my X and my E are parallel to each other, the dot product is just going to give me E dx. So delta V from A to B is going to equal negative the integral from 0 to D of E dx. So I've already found my function for E, so I can plug that in right here. So delta V from A to B is going to equal negative the integral from 0 to D of sigma over E naught dx. Well, sigma over E naught is a constant, so I can pull that out in front. So I get negative sigma over E naught times the integral of dx from 0 to D. So integrating dx just gives me x. So I get delta VA to B is equal to negative sigma over E naught x evaluated from 0 to D, which is just going to give me negative sigma over E naught D minus 0. I know it's a lot of steps, but I like to show everything so we don't get lost. Delta V from A to B is going to be negative sigma D over E naught. So that would give me my potential difference from A to B as negative sigma over E naught times D. So all I need to know to find the potential difference between those plates, which is the voltage, is the charge density and my separation distance between them. This is similar to this version where I plug in the E. Because I know it's a constant, did I really have to substitute in for it? That gives me that delta V from A to B is going to be negative E times D. And the reason that it comes out negative is simply because the electric field points in the direction of decreasing potential. So because we are going from high V, high potential, to low potential, so my electric field is going from high to low. That's what that negative. The negative here really just means opposite for that. So if I had integrated instead from negative to positive, that would have gotten me kind of the opposite. So it doesn't really matter which way you go. It's just your signs will change depending on your definition. Because if I do it in the opposite way, I would have started at D and gone to 0. So it would have switched the limits of integration, the order of the limits of integration at that point. Now, this equation is on your formula sheet. So you don't actually have to have it memorized, but you do have to realize that this is the potential for a parallel plate. It does not work for point charges or spheres or anything along those lines. Now that's one way to find the electric potential. Another way we could have done it is by looking back at kind of our definition of work and potential energy from our electric potential energy video. So remember that what we did before is we took a look at what happens if you were to take a point charge and you were to have it at the positive plate and we were to move it to the negative plate through a separation distance of D. And we went through the point that if there is some constant electric field here, now the only problem with this one was we did not actually know what the electric field was. We'd have to use Gauss's law to have derived it. But if we had that constant electric field, then we defined that our work was equal to the change in potential energy. Our work would have been the force applied over the distance. And we would have said that our work is the integral of f dx. And that was going to equal our change in potential. Actually, it was our negative change in potential. And that work was going to be based on the force. And we defined our force as equaling Q0 times E for our electric field. So we can define x equals 0 again. We're going to x equals d. So we would integrate from 0 to d. And we found that our work was equal to Q0 E times x evaluated from 0 to d, which is still just going to give us that our work is equal to Q0 E times d. Now, our potential energy, we said that because this is conservative, our work is equal to the change in kinetic energy, which is equal to negative the change in potential energy. So, well, that tells us that our change in potential energy is going to be negative Q0 E times D. And then I could use the fact that my potential is defined as my electric potential energy over Q0. So my delta V would, it's still from A to B, because we're still going from one side of the plate to the other, from A to B, would be equal to the change in my potential energy over Q0. So that delta V from A to B would equal delta U electric, which would be my negative Q0 E times D over Q0. Q0 cancels, so I get that delta V from A to B is equal to negative E times D. So you can see two different methods got me the same answer. Now, the problem with this one, the reason I would not have started with this is because it wanted it in terms of sigma, and they didn't officially define the electric field as equaling sigma over E naught. But it gets me the same answer either way.